Hi everybody, I'm Marty Geyer, your professor for your AI class, and I wanted to give everybody an opportunity for a video lecture to talk about Astar and heuristics to help you with the third week's lab. I hope everybody's started on it, gotten past this point already, but just in case, here's a quick run through of what you need to know, and hopefully this will help you implement the algorithm. I apologize for the tininess of the numbers. My whiteboard is only so big, and my camera kind of has to be where it's at. But I promise I will read everything off, and please do provide me feedback, and I can help make these video lectures a little bit better if they are helpful for you. So what we have here is a 4x4 puzzle, which is the 16 puzzle you've been working on. What I'm going to do is actually I'm going to cheat and not use that puzzle, and we're going to tear it apart a little. So 4x4, the 16 puzzle, sorry, is 1, 2, 3, 4, 5 through 16, and that's the one you're going to be working on, but it is analogous, of course, to its smaller component, the 3x3 puzzle, and also the 2x2 puzzle, which is just a simple 1, 2, 3, I don't have it written up here, but 1, 2, 3, and then blank space would be the solution state, the same as for the 15 puzzle rather, with the space at the end. So what I've done here is given you a random board state, where the space is the first position, and then we have a 3 and a 2 and a 1, and these positions like this. And what I'm going to do is solve this for you, help you solve it with the Astar algorithm. So what's going to happen here is suppose we're in this state. Now remember, Astar uses G of n and H of n. G of n is the value of movement, or the cost of movement, and H of n is the heuristic value at the particular state that you're looking at. So first thing we need to know is the basis. So where are we now? So the heuristic H of n here is the current heuristic value of this board. And what I'm going to do for the heuristic is use the Manhattan distance. The Manhattan distance, if you'll recall from the book, means it's the sum of the Manhattan distances, which is the sum of all the differences between the current position numbers and where they belong. So let's do it, for example, on this one. So on this board, 3 belongs down here, but it's up here. So it's off by 1 position. It's off by 1 position down. We don't really care which way, it's just summing up all the numbers. It's off by 1, so 3 is off by 1. Write that there. 2 is off by 2 positions, 1 up and 1 over. Alright, got a bummer marker here. I know you probably can't see the tinier numbers, so I'll read them off for you. So 3 is off by 1, 2 is off by 2, and 1 is also off by 2. 1 up and 1 over. And if you sum all those up, we get 5. So the current heuristic value of this board is 5. Now, there's 2 possible ways to go. Again, I simplified this problem in the 4x4 puzzle, remember. In this case, like for example, you have 3 possible ways you can go. In the middle 4 squares, there'll actually be 4 possibilities. In the corner, there's only 2. But there are, on average, 3 possibilities here. But on our current state here, there's only 2 possibilities. So the one possibility is move the 3 over this way, or rather move the space over this way. And you get this board state, which is 3 space 2 1. Now, what we need to do is when we're running the Astar algorithm is we generate all the possible board states. We generate these 2 board states, and I think a lot of you have already done that in your current algorithms for iterative depth first search. And then what you need to do is calculate the heuristic value of each. So let's calculate the heuristic value of this one. So 3 is off by 2 positions, 1 over and 1 down now. So 3 is off by 2, 2 is off by 2, and 1 is off by 2 as well. And that comes out to 6. Now you want to minimize the heuristic value in this case for this particular heuristic. So 6 greater than 5, this is a bad board state. We don't want to go here. Unless of course it happens to be the only state, then we don't have a choice. We'll get to that in a few. Now this board state here, the other way to go is we move the space down instead. So 2, 3, space 1. And here we have 2 is off by 1, 3 is off by 1, and 1 is off by 2, which is 4. So this is actually a better board state. Certainly it's better than this one. Really you're only comparing the 2 that you generated. So Astar would pick this board state. Now you actually want to save all your states because you could get in a situation where you get to the end and you don't have a solution. You reach a local, I guess in this case it's a local minimum, and we talked about that this week. That's always possible, and so to avoid that, or to counter for it, you have to store all the states to make sure you don't reach another state. The first step is check against your state list to make sure that you haven't already seen this state. If you haven't, then add it to your state list, evaluate the heuristic function, determine which way you're going. Actually, you don't want to add it into the state list until after you've chosen that path. So this one you will not add because you haven't chosen it, and you could have to come back to it at some point. So when we choose this state, now the solution falls into place from here. Unfortunately, in this board, it generates quickly. There's only two possible ways. The other one is to go backwards. Well, we don't want to go backwards because we've already seen that state. Also, even if we hadn't, the heuristic value is higher than our current value, so we don't want to go that way. So the other state we generate, and the heuristic here, the other state is moving the space over this way. So we have 2, 3, 1 space. And for this one, it so happens that everything is 1, I believe. Yeah. So your total heuristic value here is 3. So with this one, now, this is the better state. And I think you can see, if you eyeball this, how quickly it is if you just move the space or move the numbers around the board, you can get back to the solution position 1, 2, 3 space here. So this leads directly to the solution, which is convenient, and you solve the problem. If it doesn't lead to the solution, you want to pop back up to the initial state. We'll assume this is the initial state, and then you want to take the next path down. Even if it isn't the best heuristic, it'll be the best heuristic value of the paths you haven't taken. So first, check paths that you've taken already. If you've already taken it, then cross it off the list. Then take the optimal value, the minimum value of all the remaining states. And that way you kind of explore the whole board position. Now this will hopefully converge on a solution, especially for the 16 puzzle that you can see quickly and easily. I believe with most computing resources that will be the case, so hopefully you will be able to find the solution. Keep in mind now that because you're generating a random board state, depending on how you did this, some puzzles may not actually be solvable. So in that case, you know, it's going to run forever because it won't actually find a solution. So crafted this a little weird, you might have to start a couple of random board states until you find one that's a solution. Alternatively, you can adjust your algorithm, as I saw one brilliant student has done, where instead of generating random numbers, you simply generate a board, a solution board, I believe he did, and then you make random moves. So you have your algorithm move the pieces at random, and you do that 100,000 times, enough times the pieces are sufficiently shuffled. That way you make sure there's actually a solution state. I hope this is helpful. I don't want to give away the exact internal loopings in C++, or rather there isn't time and depth to go into that, but I think you'll be able to do that here. You can see that you're going to have a basic main loop, storing states, checking the current state against the states that you've stored, picking the optimal value, and then recursing down from there. So you loop again and do the same thing again. Remember, you have to pop yourself back up again, so be careful. I see a lot of people on the recursive cases not thinking them through. So review your iterative depth first search to make sure that's correct, so you have your recursive cases thought about. You need your base cases where you have a solution, or you've reached the end and there are no more states to check, and you have to make those a base case so you'll pop back up. And then you need your recursive case that reduces the problem or increases the, gets you closer to the goal in this case. Please let me know if you have any questions. I hope this has been helpful.